Before we get to our lesson today in our two molecules, we have to talk about something called the carbonyl group, which in fact is going to create our two molecules today. So let's do that. So aldehydes and ketones, which are the two molecules we're going to be learning about, are the first example of compounds that possess a C-double-O bond, so a carbon-oxygen double bond. And this is what we're calling the carbonyl group. And obviously it's going to have different properties than all the things we've learned in the past here. Now here it is. It's kind of tilted on its side. Another way to put it would be more so straight up like this. And there is some polarity indicated here. Your electrons are navigating more towards the oxygen end. So you're going to have a polar molecule involved here with the molecules that we're making today. And so the bond angle is also pushed around here because of oxygen and its couple of lone pairs. Okay, so the following class of organic molecules involve the carbonyl group. So the first one we're going to look at is the aldehyde. So before we even get to the definition, the aldehyde is essentially your carbon-oxygen double bonded together plus the hydrogen. So essentially it's happening at the end of a chain. So there is the CHO group, and then it's attached to some carbon chain. And again, for it to be an aldehyde, the double bond has to be on the very end, like the very first carbon has to have this doubly bonded oxygen. So here are a few examples here. And you can see in all of these examples, no matter if they are something with a multi-bond or something with a ring, that our COH is at the end of the molecule. That's what makes an aldehyde. So talking about naming these now, so the IUPAC rules. So select as the parent chain the longest continuous chain that includes the carbonyl group. It's going to be pretty obvious here. Name the parent chain by changing the corresponding alkane name that ends with the E. So E is going to change to al. So pentane, pentanal. Octane, octanal. Number the parent chain, assuming the carbonyl group is on the C1, that should be obvious here. And then if there's any substituents, we'll add those at the beginning of our compound's name. So here's our first example. And you can see that, again, our COH bond is at the end of the molecule. We'll identify that as an aldehyde. The chain is 3 long, so this one should simply be propanal. Notice the ending is AL. Now this one might at first appear a little more complex. Again, notice the COH is at the end here, which is good. You draw your carbon chain. You got 1, 2, 3, 4, 5. So this is a pentanal. And then we have to name these subgroups. So this is where you number your chain. 1, 2, 3. This is a 4th carbon. So it looks like you have a methyl group on the 4th carbon. So 4-methyl pentanal. And again, this one, again, might look complicated at first, as long as you identify this to have 1, 2, 3, 4, 5 carbons. So again, this is a pentanal. And this group here, it looks to be too long. It's got 1 there and 1 there. So this is an ethyl group, and the ethyl group appears to be on the 2nd carbon. So we're looking at a 2-ethyl pentanal. So they frankly don't get too much more complex than this. Again, there's not a lot of variation because the COH group has to be at the end of the chain. Here's some common ones, and again, the simplest ones. We got formaldehyde, which is methanal, and then you can see some of the other ones. They're just increasing by 1 CH2 unit each time. And they even get a little more complicated, so you can have this like benzene ring attached to the COH group. Again, it's at the end, so there you go. You've got your aldehyde. And here's a couple of derivatives too, so they get more complex. I like this one because it's got the bromo attached to the ring, and this one's got the hydroxy attached to the ring there. So that's all we have to say about aldehydes. Let's talk about ketones. And essentially what's going to happen with a ketone is we're going to have the double bonded oxygen in the middle of a carbon chain. So your general formula looks a little something like this. You got the CO in the middle, and then a couple of chain lengths. They may or may not be the same, and there actually ends up being 2 different ways and 2 different acceptable naming conventions for ketones. So here are some crazy examples, maybe not that crazy. Again, looking at this first one here, there is our C-double-O in the middle of our chain, and we've got a methyl group here, and we have an ethyl group here. So here, there's a couple of different ways to name this one. We'll name it in a sec. So select as the parent chain the longest continuous chain that involves the carbonyl group. And this time we're going to remove the E and add a 1 or own. So we're going to number the chain as well in case there's any subgroups. And same thing with the substituents there. And of course we'll add cyclo if we're talking about a cyclical ketone. All right, so here is our first one. So we'll put the name up and it's going to be 3-hexanone. So the 3 is telling you where on the chain it's located. The hex tells you that there should be how many? 6? 1, 2, 3, 4, 5, 6. And the own tells you that the ketone. So again, the own indicates you have this double bonded oxygen carbon. The hex tells you there's 6 carbons, and the 3 is telling you where this multibond is located. And here's another one. So you'll draw your longest chain. Probably looks a little something like that. It's got 1, 2, 3, 4, 5, 6. And we've got a methyl group coming off it. So in terms of a name, we have a 4-methyl. If you number your carbons, 1, 2, 3, 4. So we have a 4-methyl located there. And then this 2 is telling me where the C-double-O bond is located. And the O is, of course, indicating that name. This one, again, your longest chain should be 4. And it looks like we have a bromo on the 3rd carbon there. So 3-bromo. Again, carbon 1, 2, and there's your 3rd. And then don't forget we have a chain of 4 with the double bond on that 2nd. So butanone. And you can even have some of these rings as well here. So we've got a cyclopentanone. And then we've got a methyl on the 2nd group. So that would be considered the 1st carbon. That would be considered the 2nd carbon. There's even another way to name these ones that personally I like a little bit better. It considers that this is in the middle and then what groups exist on the outside here. We've got 2 carbons long as an ethyl. We've got a propyl here. So we could call this one ethyl propyl ketone. That one's easy to remember. And here's another one too. To say, okay, there's our unit there. We've got a methyl group here, and then this could be an isobutyl group. So isobutyl methyl ketone. You could also name this one as some kind of 2-methyl propyl group, but isopropyl is just as acceptable here. And now we can also have the bromo involved. So there is your CO unit, and you got a methyl, and then over here you got an ethyl, and we do have to indicate where that bromo group goes. So the bromo is on the ethyl group. So 1 bromo, and then methyl ketone. That one's a little more complicated because you probably think to yourself, well, is this one, what's it talking about? It's not really on the 1st carbon in the chain, but it happens to be on the 1st carbon of the ethyl group. So aldehyde and ketone functional groups, as we saw, alcohols can be used to create aldehydes and ketones, and oxidation of a primary alcohol yields an aldehyde. So we have to have knowledge of alcohols here as we talk about our reactions of aldehydes and ketones. So here's our first one. Now this O is just, it's standing for the possibility that it's going to be like involved in the double bond. So it's not necessarily, it is another molecule, but it's just simpler to write it above the equation here. So let's see what's going to happen. So really what we've done is we have lost this O here and this H here, and they've been put together with that HOH. Makes water, doesn't it? And then the resultant is a double bond is created here, and we have our single H still sitting there. Now what would happen if, so again, keep in mind this one that we just looked at, this was an aldehyde, right? It was an aldehyde because we had this created at the end. Well, sometimes they can get created in the middle of the chain, and that's going to happen when our alcohol is in the secondary spot. So it's not at the end of the chain. Same kind of thing is going to happen. We're going to lose that H, we're going to lose that H, and a double bond is going to form. And those 2 H's combine with that O, and we make our water. So there's the creation of an aldehyde first, and then in a second one we can create a ketone. And there's also the kind of the opposite of this, and it's called hydrogenation, easy for me to say. And so what we're going to do is we're essentially adding kind of hydrogen gas to one of these ketones or aldehydes, and we're able to lose the double bond and turn it into single bonds. So here is an example. So again, we're looking at an aldehyde. There's our aldehyde. So when we add on, or when we complete our reaction, it looks like one hydrogen is going to attach to that O. The double bond is broken, and the other hydrogen should attach to that carbon, just like that, and we form an alcohol. So this one is an aldehyde to an alcohol. There we go. Ethanal and ethanol. And we can also have this occurring with a ketone as well. And so for this ketone example, again, the hydrogen is going to go up to that spot. It's going to go to that carbon, double bond's broken. And we end up with our secondary alcohol. Now, these types of reactions, there's something you need to memorize. They're not necessarily something you can perhaps figure out. I mean, you could guess, but you really have to know the direction here. So pay attention when you see hydrogen, hydrogenation. You're thinking hydrogen, and hopefully you can, think about how that name plays into the example. So a few isomers here. If there's any question, you can have both a ketone and an aldehyde forming from the same formula. It's really just about where you put the functional group. So the CO group, the carbonyl group, it's in the middle there. Here it's at the end. So you can have some positional isomers as well here with ketones, and it's really just about moving this unit around in the molecule. Depends on the length of the molecule, how many results you're going to get. And again, it gets a little more complicated here. You can have your aldehyde and your ketone. Aldehydes are often recognizable by their sweet smell. We've got vanilla here. Hopefully you know what that is. I don't know about, we got almond flavoring and cinnamon. Hopefully that was a dead giveaway there. We also have the same for ketones. They can have a sweet example. We've got clove flavoring, butter flavoring, and spearmint. And again, these can be created simply in the lab by adding the right chemicals together, and you can smell them. And there's a wide variety of these aldehydes and ketones that you might know about. And you can even just see some of the names here. We've got glucose, hopefully you recognize. There's the aldehyde unit, testosterone, progesterone, and cortisone. And again, you're always looking for, these double bonded oxygens and whatnot. There we go. So some physical properties. Neither aldehydes nor ketones possess the ability to hydrogen bond with other molecules like themselves. Consequently, boiling points for aldehydes and ketones are lower than for alcohols, because alcohols do have the hydrogen bonding possibility. The CO double bond makes things polar. Again, we have that dipole pointing that away. So you get some polar things, so that should affect your solubility and how things boil. And here's a little chart. So we've got our alkane here for starters, and we're boiling at minus 89 degrees, so it looks like it's a gas at room temperature. Once we get up to our aldehyde, you can see it's still a gas, but it's boiling at much lower. And then our alcohol looks like it's 65 degrees, so it should be liquid. And then again, we've got some repeating values here and repeating numbers, and you can see our values are always getting larger as we increase here. It doesn't even have a lot to do with the chain length. It's more of just what's bonded there. So there's your CO and there's your O units.